तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
But remember, we were talking about finding the derivative of a function numerically that is given a set of data points. How do we find the derivative on one of those defined data points or on some other points in between? And we looked at the method in which we would interpolate, we will construct a polynomial which interpolates all these points and then find the derivative of that polynomial. So, we will first look at an implementation of this algorithm, and then we will look at other methods of finding the derivatives like the finite difference scheme, etc. Okay, so, this is something which you have looked at in the last few classes. That is we have set of points given by x0, x1, etc., and we have the function values of those points, and then we find out the polynomial which interpolates that set of data points, or the set we have a polynomial which goes through all those data points, and that polynomial of order n is defined in this fashion using the Newton scheme. And I guess you remember that these points f x0, x1, f x0, x1, x2, coefficients of the first order, second order term, etc., can be obtained by constructing a difference table. Okay. So, that is what we would be looking at. So, I will just write down this difference table once again, and then we will look at the implementation of this algorithm to find the derivative. Once we have the difference table and we have the coefficients, right, and then we can construct the derivative simply by this method. So, that is, we write now the derivative as again in terms of as another polynomial, and this you look at that this terms now become slightly different. For example, the first order term, there are two of them, right, and similarly there will be the nth order term, there will be n plus 1 of them. Okay, so, that is n plus 1 sums in the nth order term. N minus 1 term will have n such sums. So, that is a polynomial, and we will just look at a program which calculates this for a given function. So, before we look at the program, let us look at this coefficients of the polynomial once again. That is, we will construct the difference table and then look at how we get this coefficients. So, that is listed here. So, we have I have listed here 5 points, for example. So, 6 points. So, that is 0, 1, 2, 3, 4, 5, and these are the tabulated x values. Okay, need not be equidistant. It could be any 5 values. Okay, so 6 values x0, x1, x2, x3, and x4, and these are the function values. Okay, so now this terms in the square brackets are the coefficients of the polynomial. Right. So, we have the function value here, and then the next term would be the difference between these function values divided by x1 minus x0, and the difference between these function values divided by x2 minus x1. There is a first order divided difference, what we call the divided difference, the first order divided difference, and then you have the second order divided difference, and then you could write the third order divided difference here as x0, sorry, x1, x2, x3 minus f of x0, x1, x2 divided by x3 minus x0, etc. Okay, so you could write down them, all these points. So we could construct a divided difference table like this, and then we can read off these points. Okay, we have done this earlier in the case of polynomial interpolation. This is exactly the same thing. And also notice the way we construct the polynomial here, okay, is we just write down this as first order term, second order term, and similarly up to nth order term, okay, for an nth order polynomial. Okay. But we need not write it like this. We know that we can write it in a nested form, that is starting from the nth order term. We could write it as in a nested form. We have seen that earlier. Okay, so we could write the polynomial Pn of x, if you remember, as f of x0 plus f x0 x1 into, right. So x0 minus x plus f of x0 x1 x2, etc. Right. So we could write this in a nested form like this. We have seen this earlier. So that's what we would see in the program first. Okay. And then, however, but when you go into calculating the derivative, it's convenient to write it down in this fashion. Okay. So it's convenient to calculate the derivative by writing it down as separate functions, separate terms for each first order, second order, and higher order terms. So here is a program which would implement this particular algorithm for the Newton's form of the polynomial. So what we do is we just take a function x of I as a f of I, which is exponential x. Okay, so that's a function which we are going to do. So what we do is we take this function f of x, which is e to the power of x, and then we will tabulate this function in a set of discrete points, and then we will construct a polynomial which goes through this set of tabulated points and calculate the derivative. That way we can actually compare it with the derivative of this function, which is that function itself. Okay, that's an easier comparison for demonstration purpose. So we first calculate the first part of this program is actually just calculating that or tabulating that function. So a function is exponential x. Okay, so I just take a set of equidistant points. It need not be equidistant in this particular case, but we just take for convenience a set of equidistant x values. So starting from 0 to n, so there are n plus 1 such points. So where n I fixed as 6, so it will be 7, so 7 tabulated points. And then we have the function value at those points, which is given by exponential x. Okay, and just print them onto a file so that we can compare it with the interpolating polynomial. And then here I compute now the divided difference. Okay, so I compute the divided difference into a two-dimensional array. Okay, so this is the first term. So I is the index of these rows. So I have computing this into this divided difference into a two-dimensional array. One index for these rows, these columns, and one index for these rows. So the first index here is for the columns. Okay, that is, this is the first order divided. This is divided difference, which is starting from 0, and when this is 1, that is a second order divided difference, etc. So here this is the 0th order divided difference would be just a function itself, and the first order would be the difference between the function divided by x1 minus x0, which is one interval, and then the next would be, okay, sorry, here I have to write x2 minus x0, and here similarly x3 minus x1, and this is x4 minus x2, and this x5 minus x3 at the second order divided difference. So this is the index for the order of the divided difference, and this is the index I, which tells you how we run through all the columns. So that's the first. So the divided difference is actually tabulated into this two-dimensional array dt. Okay, so that's first I constructed the 0th order one, and then I go into a loop which is j going from 1 to n. J goes from 1 to n, so 0 is already done. So this is the order of the divided difference. We have n points tabulated, so we have up to n order in the divided difference. We have n plus 1 points tabulated. We have n points in the n order in the divided difference. Okay. So, n plus 1 because it goes from 0 to n, and so I have n plus 1 order divided difference starting from 0 to n. And then so that this is the construction of the divided difference. So, I take for each order. Okay, so, the number of elements in that divided difference will be n minus j. Right. So, each order j. So, if you take the 0th order, I have n divided difference points, that is 1, 2, 3, 4, 5, 6 here, okay. And I take j equal to 1, that is the first order, then I have only 5 of them, that is 1, 2, 3, 4, 5, and then I take the third order, second order, I will have only 4 of them, okay, 6 tabulated points, so there is only 4 of them, etc. So, that is, you go from I starts from 0 to n minus j. So, that is this loop, and I compute the divided difference for each order. So, once I have that's the difference between the previous order divided difference divided by x I plus j minus x of I. Just notice that x I plus j minus x of I. So, the denominator keeps increasing in distance as we go along. Here I have ignored the fact that this is equidistant, and we know that if the points are equidistant, we can simplify this procedure. I am just writing a general program which is actually works for any tabulated set of tabulated points, not necessarily equidistant. So, once you have that divided difference, now we can compute the derivative polynomial and the derivative. So, the reason why I did this is a 2-dimensional array instead of just a 1-dimensional array, which we have done in the polynomial interpolation. Remember, in the polynomial interpolation, we actually computed this divided differences into a 1-dimensional array. The reason being that we actually need to store only one set of divided difference values. Okay, so, if you always enter the divided difference table at the top. Okay, so, if you are always entering the divided difference table at the top, that is, we can evaluate a function value at any points starting from x0 to x5 or in between any points using this polynomial, which we wrote as Pn of x, by entering the divided difference always at the top, or we could also enter somewhere in between. So, if you are entering it always on the top, then we will be using only this set of values. Okay. So, we will use only this set of divided difference values. So, we need to store only that. Okay. So, I need only a 1-dimensional array to store that. That is what we had done in the polynomial interpolation case. But here we want to have a little more freedom, that if I want to compute as we saw in the last class, that if you want to compute the derivative of this function, okay, anywhere in between two tabulated values. Right. So, we want to have the freedom that I want to enter the difference table at this point. So, for example, if I want to compute the derivative at any x in between x3 and x4, I should have the freedom to enter the difference table at x3 or x2 or x1 or x0 anywhere. So, that is the reason why I store this divided difference here into a 2-dimensional array. Okay, so, just to get that freedom for that. Okay, so, here is first we will just calculate, just to see everything is correct. So, first we will calculate the polynomial itself. Okay. So, now the polynomial is constructed here. So, there are 3 loops, okay, as you can see that the polynomial construction now involves this finding the product of x minus xi. So, for the nth order term, we will have to find the product of n x minus xi, that is x minus x0 into x minus x1 into x minus x3 up to x minus xn minus 1. Right. So, we have to find that product first, and then multiply that by the coefficient, okay, and then add it to the next product and multiply it by the next coefficient, etc. That is what we have been doing here. Okay, so, if you look at this, so first I will find I will start with, so now computing this value, this polynomial values at starting from 0.6 to 4.5. So, we have the function tabulated from 0 to 5. Okay, that is the function tabulated. So, we have starting from x0 equal to 0 to when I equal to n, we have 5. So, x0 to 5. So, we will evaluate the polynomial, we will construct the polynomial and evaluate it at the other set of values, that is starting from 0.6 to 4.5. So, now if I take an x value and if I want to evaluate this polynomial now, I am not writing this in a nested form, I am writing term by term. So, sorry, this is not term by term, this is the nested form. So, I start from the last term, that is d, the highest order divided difference, okay, that is dt of k comma 0. So, remember here I am entering the difference table from the top. Okay, so, I am entering it on the top. Okay, so, all the row is the 0th row, for every column is the 0th row, that is every column the top element is my coefficient. Okay, so, I start from the highest order. Okay, the highest order is k. The highest order I start from the k, that is for the last term, that is k equal to n minus 1. Okay, that is my highest order. So, I start from there. Okay, actually highest order is n, sorry, highest order is n. Okay, I start from there. So, I start y as the highest order coefficient, and then I find the product of that with x1 minus x of k. Okay, x1 is the point at which I want to evaluate the polynomial, okay, and then I add this term dt, the next coefficient. Okay, so, let me write this thing, then it becomes clear. So, the way I am constructing this polynomial is backwards. Okay, so, I start with my highest order divided difference, that is x0, x1 up to xn. Okay, that is my highest order divided difference. Okay, and then I multiply. I am multiplying this with x minus xn, and then I add to this another term which is f of x0, x1 up to xn minus 1. Okay, then I put a bracket there. Okay, and I multiply this by x minus xn minus 1. Okay, and then I add another term which is f of x0, x1 up to xn minus 2 as the next coefficient, okay, to this, and then I put a bracket there, that is another bracket there, and then I multiply this by x minus xn minus 2, etc. So, I continue it this way till I reach f of x0. So, that is the way I am constructing. So, I am going it polynomial like this. Okay, I am constructing it in this fashion. So, starting from the last term and I am constructing it backwards. So, this is the nested form of the polynomials. For each term you add, you have to put in one more bracket so that this term is actually the nth order term in the polynomial. Okay, because it get multiplying by x minus xn, x minus xn minus 1, x minus xn minus 2 till it reaches x minus x0. Okay, so, that is what this will be. So, there will be n, sorry, this is n minus 1, this is n minus 2, and this is n minus 3, etc., till it gets x minus x0 at the end. So, this will be then by the time it reaches x minus x0, this term would be multiplied by x minus xn minus 1, x minus xn minus 2, x minus xn minus 3 up to x minus x0. Okay, that is a implementation here. So, you start with the highest order divided difference, okay, and then you multiply that, this y is now just this highest order term, multiply it by x1 minus xk, k is n minus 1 to start with, add the next order term, that is n minus 1 0. Okay, this is always 0 because we are on the top of the divided difference table, and now that becomes y, and to that y now you multiply the next term, that is n minus 2. So, x1 minus xn minus 2 and add the next divided difference, that is n minus 2 0, etc. That is a nested form of the divided difference table. So, that will give you the polynomial, and I write down the function, the value at which I am evaluating it, and the polynomial value to a function, to a data file called Newton.dat. So, that we will just see that we will just run this. Okay, so before we run this, I just want to show you one more thing. So then after we evaluate this polynomial, now we have the polynomial and the set of data points, and then I want to evaluate the derivative at any point. Okay, so we have to actually enter, the program would wait for you to enter which value at which value you want to evaluate the derivative. Okay, so that is, this x d is the value at which I want to evaluate the derivative, and d k is the number, is the point at which I want to enter the difference table. As I said that if I want to evaluate the derivative at any point, let us say between x 2 and x 3, I could enter the difference table at x 2, x 1 or x 0. Okay, so it waits for this index to be given, okay, and at what value you want to evaluate the derivative, and at what point you want to enter the difference table. So these are the two things you have to see. Okay, so we'll just look at the. Okay, so that's the tabulated value. Okay, so it's 0, 1, 2, 3, 4, 5, 6. So there are 7 points. So these are tabulated x values, the tabulated function values, okay, of exponential x. So what I was trying to tell you is that if I want to find the derivative, let's say 2.7, okay, of this function, if I want to find the derivative at 2.7, then I should be, and I can enter the difference table at n equal to 3 or n equal to 2, n equal to 1 or n equal to 0. I can't enter at n equal to 4 because then that will exclude 2.5 to 3.3 term, all the values from 2.5 to 2.3. But I can enter anywhere earlier. Okay, so that's what we'll be doing. Okay, so if I run this program, okay, so it waits for the x values. Let's enter it as 2.7, and then let's say we'll enter the difference table at 3. So that is 0.3. Okay, so it says that the derivative of the function at 2.7 is 16, which is off by a large amount. Okay, so it's clearly off. 2.6 is not exponential. 2.7 is not 16. We know that. Okay, so it's really off, because now what we have done really is to find the derivative at 2.7. We have entered the difference table at 3. Right. So we are constructing a polynomial which is basically linear. So we are constructing a linear polynomial. Sorry, in this case not linear polynomial. We are constructing a polynomial which is of order 1, 2, 3, 4. That's order 3. Okay. And then we are finding the derivative at this point. Okay. So it seems to be off by a large margin. So, but this will keep improving as we enter at earlier and earlier points. As we can see that if I enter the same value, evaluate the derivative of the same value, but I enter the difference table, let's say at 1, okay, or it's 2, let's say. Okay, so we get a slightly better value, that is 15, and now if I enter at 2.7 and if I enter at 1, I get a slightly even better value, 14.9, but you can see it's fast converging into the correct value. Okay, so how are we computing this derivative? So it's here that you enter the value at which you want to compute this, and the point at which in the difference table you want to enter. Okay, and then this function now has to compute now 3 terms. Okay, so I will show you that. Okay, so it has to compute this product, right, for every term. Okay, so for the last term, that is the nth order term. So we have the n plus 1 nth order term. Okay, so we will have some n minus 1 such sums. Right. For example, the second order term, the coefficient, the second order derivative, so the divided difference, you have 2 first order terms. Similarly, the n plus 1th order divided difference, you will have n minus 1 sums of n minus 1 order terms. That is, we will have x minus x 0, x minus into x minus x 1 up to x minus x n minus 1. Now we divide that by x minus x 0, x minus x 1, etc. Okay, so you will have a term, a table like this. So basically, so we have to compute this term. Okay, so we have seen this earlier. So we are writing down the derivative of the polynomial in the Newton's form, here. So, the first order term will now become a constant, and the second order term becomes now a first order term because it is a derivative, but then there are two such terms. Similarly, the n minus 1 nth order term of the polynomial n will now become an n minus 1th order term because we are finding the derivative, but then there will be n minus 1 terms in that. Okay, so, that is the n minus 1 terms inside that function itself. Okay, so that is what we want to evaluate. Okay, so, remember that if you have a polynomial, a term in the polynomial as say let us say a term in the polynomial, so of many terms, and then we have one term which is some coefficient times x minus x 0 into x minus x 1 into x minus x 2, etc. Now, if I take the derivative of that, the derivative of this polynomial will now have this term as a into, so we will have many terms again, and then we have a into, so we will have first derivative of this x minus x 1 into x minus x 2, then we have plus x minus x 0 into x minus x 2, and then we have one more term which is x minus x 2 x 0 into x minus x 1. Right. So, the third order term in the polynomial will now the third order term in the polynomial will now become a second order term in the polynomial in the derivative, but there are three such sums. Right. So, that is we have to program it this way. So, instead of writing for each term like this, we have a general formula. So, which writes this term particular term as, so again this particular term we will now write slightly differently. We are saying that we can write it as a product of three terms divided by x minus x 0, x minus x 1, etc. Okay, so, I will write this particular term as so we will write a into, so we will write x minus x 0 into x minus x 1 into x minus x 2. Okay, we will write it like that, and then we will write it as sum of, let's not space there. So let me write this again. So, the derivative, so we had a derivative of the function, so that had so it is a first order term, so we will have some term first order term, and then we had a term which is a x minus x 0 into x minus x 1 into x minus x 2 plus a plus x minus x 2 and then we had x minus x 1 into. So, we had these three terms, right, and then we may have higher order terms. I am just writing concentrating on the third order term. So, this I can write as a into x minus x 1 into x 0 into x minus x 1 into x minus x 2 into 1 by x minus x 0 plus 1 by x minus x 1 plus 1 by x minus x 2. Okay, so that is what I can write it as. So, that is x minus x 0 term, this x minus x 1 term, sorry, this is x minus x 0 and x minus x 1. Okay, so, we have these three terms written as in this fashion. Okay, so, I have a product here and I have a sum. Okay, so, that is what I am trying to do here. Okay. So, I will have a product and a sum. So, this product first which can be come out of the sum, okay, and then a sum of 1 over x minus x I and multiplied by the corresponding divided difference coefficient. Okay, that is what this term is doing here. So, I have a sum of x minus x i's here. So, again the dk is the point at which I enter the polynomial. Okay, so, that is also important. Okay, so, I need to know which point I enter in the divided difference. So, it is not always be on the top. Okay, so, that is the sum which I do 1 minus I do a sum of going from 0 to k of all the points which is that is order of the term, right, that is order of the term in the polynomial or the derivative polynomial, and I have the sum here for that term, that is 1 plus x d with the point at which I enter x minus x I or x I plus dk, because dk is the point at which I enter the polynomial, and then there is a product here. So, first I find the product x minus x I, and then I take the sum, which is 1 by x minus x I summed over all the i's, and then I take the product of that sum and this sum and this product p r and y. I take the product here and multiply that by the coefficient, the corresponding divisor difference coefficient. Okay. So, now it comes to be k plus 1. So, we have said what point you want to enter the divisor difference. Okay. So, when you run the sum, how many terms will be there in this polynomial, it depends on where you enter, right. So, if you are entering on the top, that is dk is 0, okay, then there will be n terms in the polynomial, because it is an nth order polynomial, you will have n terms in the polynomial, right, and then the derivative you will have n minus 1 terms. Right. And here, so that is when if you enter on the top. Now, if you enter anywhere in between, so if I say in the case of 2.7, we saw that we could enter it at 4, 3 or 2 or 1, 0, etc. So, if you enter at a later point, that is somewhere here, okay, and then you will have only that many terms in the polynomial. Right. For example, if I enter this point, then I will have a term in the polynomial, I will have a term containing this, and then 0, 1, 2, 3, 4, 5, etc. There will be 5 terms. Okay. But if I enter here, for example, then I will only have 1, 2, 3 and 4 terms. Okay, so, I will have less number of terms as you come, actually only 3 terms, sorry, 1, 2 and 3 terms. So, and as if you enter here, you will have only 1 and 2 term, and if you enter this point, then you have only 1 term in the polynomial. So, as you enter the later in the difference table, you have less number of terms in the polynomial. Okay, so that is what is reflected here. So, this is basically the total number of points in the polynomial, which goes from n minus dk minus 1. So, if dk is 0, it goes from n minus 1 to 1. Okay. So, actually it goes to 0, the 0 is added separately. So, n minus 1 to 1 in this term it goes, but if you enter later, okay, then you have less number of terms in this sum and in the polynomial. So, I find the product of each term for each term, and the sign is multiplied by the corresponding divisor difference coefficient, and I get the derivative, and the last term is added separately here as 1 plus dk, 1 dk, the last coefficient, and then I print out the derivative, and that is what we just now saw. Okay. So, basically it is the same thing. So, if I do this polynomial derivative, I am just constructing it in this fashion. Okay. If it is a third order polynomial, and this will be my fourth order polynomial, sorry, if it is a third order polynomial, this will be my last term, there will be a second order term, and then there will be a first order term, and then there will be a 0th order term in the polynomial. Okay, that is what we just now saw. So, you can plot okay, so you can plot this polynomial as we seen earlier. So, what I have done is now I have the square points as my tabulated values. Now, I constructed a polynomial which goes through that, okay, and then I am evaluating the derivative at any point I want. Okay. So, I could evaluate the derivative, for example, we took at 2.7 somewhere here, okay, by using the polynomial which starts from here and going all the way end. Okay, I could even stop it at there. Okay, I use it all the way up to the end. Okay, or I could use a polynomial which starts from here and goes all the way up to that. Okay, I could use a full polynomial, or I could only use a part of the polynomial construction. Okay, that is what I have here just now seen. Okay, so now we can use the same program which we just now saw. We could use the same program to actually construct the derivative using the method of where instead of using the divisor difference, we could use the deltas. That is, we do not use this denominator. Instead of using a divisor difference, we just take the difference. Okay, that is we don't use the denominator here, okay, and that we can do in the case where points are equidistant, okay, that is x1 minus x0 is equal to x2 minus x1 equal to x3 minus x2, etc. So then the same program can be used, but we could write the divided difference slightly differently, and that's what we have seen in the earlier class. Okay, so we'll see an implementation of that in a later class. Okay, right now we will go into the difference formula, which we started discussing yesterday, and then we look at how to construct now, instead of a polynomial, how to write down a difference formula for the derivative. That is, the question was that if I want to evaluate the derivative of the polynomial, if I want to evaluate the derivative of the function at any point in between the tabulated values, then I need a polynomial. I need some smooth function. So as I said, that you could have the derivative by approximating the set of discrete points by a smooth function and finding the derivative of that. Okay, that's a method which you use if I want to evaluate the derivative at a point in between a set of tabulated values. But if I want to actually evaluate the derivative at the tabulated value itself, then I could construct that by writing down a discrete formula for the derivative, and that's what we call the difference formula. Okay, so writing the derivative as a difference formula. So derivative of function as a difference formula, and that's what we saw. One thing which we saw yesterday. Okay, so we will continue with that and write down and see how to construct difference formulas using a general scheme. Okay. Again, based on the polynomial interpolation idea. Okay, that's what we will look at now again. So as I said just now, that if I want to write down the derivative of the function at one of the tabulated points, and then we could enter the polynomial at a value, at the same value, and then construct the polynomial. That is, if I want to evaluate the derivative of the function, okay, in this function at, let's say, x3, okay, if I want to evaluate the function, the derivative of the function at x3, then I could enter the polynomial here, okay, at this point, and then construct and then look at what the derivative is. So we will do this in the case where the points are equidistant. So when the points are equidistant, we have seen that we don't need to write this difference formula in this fashion. Okay, we did this in the last class, that we can write them as just the differences can be now written without just the differences, not the divided differences, and then we can construct this f from the what we call the deltas. Okay, so we call this as now delta, and this is a del squared, etc. And we had an I here to tell you where in the polynomial which we are entering. Okay, this is del I3. So that's so all these things now becomes just del, okay, just the difference, not the divided difference. So we use this notation to distinguish between the difference and the divided difference. So now this is just the difference of the functions, and the value of the functions. So that will be this will be actually deltas, and this will be this in the first order, and this will be the difference in the del 2s. Okay, that will become del 3. Okay, and using this we could actually construct the polynomial, and the polynomial we know that would look like s into s minus 1. So I don't have the polynomial here. So we'll have the polynomial now a Pn of x at any point. So actually, as we saw, as f of x0 plus s into delta plus s into s minus 1 by 2 into del 2, etc. Okay, so we could write it the polynomial in this fashion. We have seen that earlier. So then we can construct from this polynomial the derivative of that with respect to x, and we have seen the x. Now instead of using the s here, again to remind you that s was x minus xi divided by h. Now h is equal to xi plus 1 minus xi. difference between any 2 points which is the same, because it is an equidistant set of points. Okay, so xi plus 1 minus xi. So that is what we had. Okay. And now we have, so we could write this thing, everything in terms of s variable, and we know that the derivative of this with respect to x is, when we wrote dpn of x by dx, we wrote it as ds by d. So we wrote the d by ds of Pn of x, because as you can see this is written in terms of s into ds by dx, and we know ds by dx is simply h 1 over h. So this becomes 1 over h into dpn by ds. Okay, so that's the formula which I have written. Okay, so if you do that, if you substitute that polynomial into that formula, then we will get it in this fashion, right. So that is what we get. The first term would be this one, and the second term would be the minus sign, so that will be del square by 2 etc. if s equal to 0. Okay, so that is, if I find the derivative by entering, if I derivative at any point by entering at that point. Okay, so if I evaluate this derivative at some I value, okay, and I evaluate this ss at that point, starting from that point, that is, I start the difference table from that point. Okay, I enter the polynomial sorry, not the polynomial, the derivative. Okay, the derivative by entering at the polynomial at the difference table at I itself. So I evaluate this at xi, okay, by entering the polynomial at xi at the difference table at xi, then it will become xi minus xi by h, it becomes 0. Okay, and then my derivative, the first term would be delta, the derivative of this with respect to s, right. This first term would be delta, and the second term will have only a minus 1 term. So minus 1 minus delta square by 2 etc. or delta 2 by 2 etc. That is what we have, alternating plus and minus sign. Okay. So this is what is summarized here. So that is a difference table which we had, and then we went on to construct the higher order derivatives. So we said that, okay, now I can write it in two different forms, that if I enter at s equal to 0, and if I look at only these two terms, okay, and then I have this as in this fashion, that is del fi and del 2 by 2, okay, that is only two terms, okay, and then I can get a difference formula from this. Now substituting for delta fi and delta 2 fi, okay, I can get a difference formula of this form. Okay, remember, delta fi is fi plus 1 minus fi, and the delta 2 is the difference of the first order differences, so from the difference table. So then I can construct a function like that. Okay. So then if I can do better, that, or so then I get an order of h square accuracy in this difference formula, using evaluating the function at 3 different points, I plus 1, I and I plus 2. But it turns out that if I enter the polynomial at I minus 1 instead of I itself, that is, if I want to find the derivative at 3, I enter the difference table at I minus at 2, okay, and then my s will become xi, x will become s will, sorry, this is xi minus x. Okay, so if I sorry, xi, that's correct. Okay, so if I enter the polynomial at xi minus 1, okay, and then this is xi, so if I then it will become s become xi minus xi plus 1 minus xi by h, okay, which is 1. Okay, so I could, instead of entering at 3, I could enter at one value earlier. Okay, so that is, this will become I minus 1. Okay, I don't enter the polynomial at the difference table at I enter at I minus 1 and evaluate the derivative at I. Then s is xi minus xi minus 1 divided by h, then that will become 1. So s becomes 1, and the formula becomes even simpler. For the same order of accuracy, you could get by entering at xi minus 1 a difference formula of this form, which is fi plus 1 minus fi minus 1 by 2, that's the order of h square. So that's called, the earlier one was called, so this is what we call as the forward difference formula, okay, and this of second order accuracy, forward difference formula of second order accuracy, and here is again a formula of the derivative in terms in terms of the function values now at I plus 1 and I minus 1, which is again of the order h square accuracy. Okay, and this is called a central difference formula. Okay. So that is what we see in this case. So we are now converting the function, the derivative, into a set of discrete values. But remember, if you write down these formulas, okay, as we see, we need to have the values of the function tabulated at equal intervals. Otherwise, this is inaccurate. This cannot be constructed. Okay. So that one has to remember that just having a set of tabulated points and taking the difference is not enough. We need to have the function values tabulated at equal intervals to write the difference formula for the derivative, and that we could construct higher order derivatives using the same scheme. Okay, so here is a general scheme for constructing the higher order difference. So as we said that, so we will write down a general formula. So to write down the the difference formulas for higher order derivatives. So what first we saw is the first order derivatives. So first order derivatives, we saw that we can have a central difference formula or a forward difference formula, okay, either of them using a second order polynomial or a first order polynomial. Okay, we can have a forward difference formula or a central difference formula, and then now we will look at higher order derivatives. Okay. So higher order derivatives can be obtained in the following form, that we just write down a general operator for finding the derivatives. So by constructing these variables, this e and delta. Okay. So delta we know is just f of xi plus 1 minus f of xi. From the difference table we just saw that it is just f of xi plus 1 minus f of xi. And then we have now a so what is called a stepping operator e, okay, which takes the function f of x and then gives a value at f of x plus h. Okay. Let's assume that there is a stepping operator e. So our idea would be to relate e to delta. Okay. So delta is f of xi plus 1 minus f of xi, remember. Okay. Delta f is, so delta acting on f is f of xi plus 1 minus f of xi, and e acting on f is taking f to f plus f into x plus h, f of x plus h, or e of f of xi is for equally spaced data, a e into f of xi is equal to f of xi plus 1. Okay, so now we can use that. So these two conditions that we just wrote down. So what we said was we had one function called delta f of xi, delta f of x I, yeah, which is f of xi plus 1 minus f of xi, and then we said that we have something called e f of xi. So e acting on f of xi will give us f of xi plus 1. Okay, so that's something which you should remember. Okay, and then I can now write delta f of x. Since f of xi plus 1 is f of x plus h, delta f of x is basically f of x plus h minus f of x, right. So that's what it is. So this is nothing but so I can substitute this here, okay, and then I can write delta f of xi as f of xi plus 1 is e into e times f of xi minus f of xi. Okay, or now we have a relation that delta is equal to e minus 1 or e equal to 1 plus delta. Okay, that's a relation which we get. Okay. So we have a stepping operator e which is related to delta by this formula, e equal to 1 plus delta or delta equal to e minus 1. Okay, so that's what we are going to use that. Okay, so we have this stepping operator which is 1 plus delta. So we can use this cumulatively, that is, if you use this stepping operator n times, then f of xi will go to f of xi plus n. Okay, so that's the cumulative use of that. Okay, and then we will define a derivative operator d, and that's what we are going to use to find all the higher order derivatives. So let's look at the first order derivative first. Okay, so derivative operator acting on any function f of xi. Any function f at xi plus s, right. is simply the derivative d by dx of that function at I plus s. Okay. Now, I know that f I plus s is d by dx of f of f at I x I plus s is e to the power s, at e acting on s into f of x I. Remember, right? S is remember s is an integer now in this case, so which is x minus x I by h. Okay, so again we have to enter this, all these things is valid only when we enter the, or we want to evaluate the derivative at one of the tabulated points, that is this s has to be an integer. Okay. If s has to be an integer, then x has to be one of the tabulated values, right. So that is the point. Okay. So s is x minus x I by h, h is the difference between two nearby tabulated points. Okay. So this has to be an integer, that is x has to be one of the tabulated points. Okay. Then I can write it in this fashion: d derivative operator acting on f at I plus s is equal to derivative the d by dx of the stepping operator acting s times on f of x I. Okay. Okay, so now we have that. Okay, then we can now write it in this fashion. So I am repeating that again. Okay, so now I know that d by dx can be replaced by d by ds into ds by dx, and we just know that ds by dx is 1 over h. Okay, we just saw all this. So this 1 over h into d by ds of E s f of x I. Okay, so this has been d by dx has been replaced by d by ds. Okay. Since s is x minus x I by h, okay, d by dx I can write as d by ds into ds by dx, and s is x minus x I by h, so ds by dx is 1 over h. We just saw that. Okay. So now I can substitute all this into the formula to get a divided difference formula. Okay, so that's, sorry, a difference formula for the derivative. So let's see how we'll do that. Okay, so we use this following property, that is the derivative of log of e to the power of x f of x I. Okay. I can write this as d by ds of, so I can write the log of e to the power of s f of x I as log e to the power of s plus log f of x I, but f of x I is just a number. Okay, so it is same as log of e to the power of s, right? Okay, so what I am trying to say is that I write d by ds of log e to the power of s into f of x I, okay, which is same as d by ds of log e to the power s plus log of f of x I. Right. So, but this is a constant, so this is same as d by ds of log e to the power of s, which is nothing but d by ds of s log e. Okay, so that's equal to log e. Okay, so that's what it is. Okay, so it's just log of e. So d by ds of e to the power of s f of x I is just log e. So then, but if I just only look at this part, this is log of derivative of a log, that is 1 by the argument multiplied by the derivative of the argument, that is this 1 over e to the power of s f of x I d by ds of that argument, right. But d by ds of e to the power of f of x I, okay, as thus, that is this part is log e into e to the power of s f of x I. So I am using this formula. So I basically use that d by ds of log e to the power of s f of x I is log e, right. And I also write d by ds of log e to the power of s f of x I as 1 over e to the power of s f of x I d by ds of e to the power of s f of x I. And then from this I am saying that d by ds of e to the power of s f of x I is e to the power of s f of x I into log e. Okay, so now how am I going to use this? Okay, so then for s equal to 0, okay, now sorry, again we need to do that. So we just said that d of f of fxi, right? So d of f xi plus s we said is 1 over h d by ds of e to the power of s f of xi. Okay. But we are saying d by ds of e to the power of s f of xi is log e to the power of s f of xi. Okay, so let's write this. Okay, so we are saying that d by ds d by dx of, so what you want to write was sorry, d of f of xi plus, so you want to write d of f of xi plus s. We will write that as d acting on e to the power of s, that is d by dx of e to the power of s f of xi. Okay. And that is, we wrote that as 1 over h times d by ds of e to the power of s f of xi. Okay. Now we are saying d by ds of e to the power of f of xi is what we are going to replace by this function here, that is log e to the power of s f of xi. Okay. So we are going to replace this by this as 1 over h as log of e to the power of s f of xi. Okay, that is d of f of xi. So d of f of xi plus s is 1 over h. So d of f of xi plus s is 1 over h log e to the power of s f of xi. So for s equal to 0, the derivative of the function at xi is equal to 1 over h log e times e into f of xi. Sorry, log e into f of xi. Okay. So d f of xi is 1 over h log e into f of xi, or d from this I can write so from this expression for s equal to 0 I can write d f of xi as 1 over h log e into f of xi. Or the d as operator we write as 1 over h times log of e. That is a d operator is. Okay. And we know e is 1 plus delta, so I can write it as 1 over h times log of 1 plus delta. So d acting on any function is 1 over h times log of 1 plus delta acting on that function at any value xi. Okay, so that is a point, okay, which you want to write. Okay, now if I want as higher order derivatives, I simply have to write it as d to the power n f of xi and act this n times, that is 1 over h times log of 1 plus delta acting on to the power n acting on f of xi. Okay, so that's the formula. Okay, and then I can expand log of 1 plus delta, okay, in a series, and I can write that expand log of 1 plus delta. For example, d of f xi is this, which as what we just concluded. Okay, but I can expand this log of 1 plus delta and keep it on to any accuracy in delta. Okay, so I can use this difference table, okay, and I can expand this log of 1 plus delta, okay, and I keep any delta of any order I want. Okay, and that's the idea which is used to construct higher order derivatives using the difference table. So, and then we can write down the difference formula for any order in the derivative consistently, starting from this operator, which is 1 plus delta. D is 1 plus 1 over h 1 plus delta. Okay. So we stop here and then look at, in the next class we look at implementation of this in a program, and then we start discussing integration and the integration of a set of discrete points.